Um, Thank you. Our today's class is on moles, a very important topic in chemistry. And with mole, two other factors are closely related to. They are molar mass and molar volume. So, our today's topic is together mole, molar mass and molar volume. So now let's start with mole. What is mole? Mole is really a very simple thing, a simple fact in chemistry. Mole is used to measure certain amount of substance. This measurement is by counting, mainly by counting, and we can also measure mass of mole, measure volume of mole if this is gas. How is this? Let's check. We want to relate this mole with something we already know, that is dozen. 1 dozen makes 12. 12 makes 1 dozen. Let's write 1 dozen equals 12. 12 of what? 12 of anything makes 1 dozen. Suppose in my pocket I have 12 pens. How many? 1 dozen. This 1 dozen can also be big things, some big things. Suppose 12 planets together is 1 mole. 1 dozen. Yes, 1 dozen. So 1 dozen could be small thing or big thing. The number is the fact. Main fact is the number. If this is 12, we can call this 1 dozen. Clear? If you have 11 of anything, can you call this 1 dozen? No. Even 13? No. 1 dozen is closely related to the number 12. If this is more or less than 12, you cannot call this 1 dozen. So how come? If this is 24, 2 dozen. If this is 6, could be half dozen. Yes, they are. So this we really know. This 1 dozen actually is a set, is a group of certain number. This number we use, this set we use when you go for buying bananas, eggs, etc. But this cannot be used for here. Consider a little amount of water here. Water, water consists of water molecules. How many water molecules are here? How many could be? How many molecules of water could be here in little amount of water? Can you answer this? Can you guess this in dozen? No. Actually, even the water is there, this small sample, the molecule number is really huge. Because these are very tiny particles, the number of molecules they are really so big number. Dozen, not dozen, even thousands, billions cannot be applicable when you go for counting this number of molecules in water. That means here we should use, and we can use another set. It's a big set of a very big number that we call 1 mole. I write 1 mole equals 6.02 into 10 to the power 23. So one of the scientists named Avogadro discovered this number, calculated, established this number. So following his name, we can call this Avogadro number. So what is this? I make things clear again. When 12 of anything together, we can call this 1 dozen. When this number 6.02 10 to the power 23 of anything, no, anything cannot be so big in number. This can be possible for the tiny particles only. When you count for atoms, number of molecules, number of ions, then you can use this expression, this number. Because even in a small sample, the number of particles are really so huge because they're tiny. No, they're tiny. So we can use this number to represent what is mole. It's quite similar with this dozen, just number is different, number is big, and application is also different. The first one we use to buy bananas, and the next one we cannot use to buy banana. This is more relevant to number of tiny particles. Come on, I show you more examples. 1 dozen banana. When I write 1 dozen banana equals 12 banana. 1 dozen banana equals 12 banana. Clear? That you know already. And I'm going to say this, 1 dozen, not banana. This time we got hydrogen molecule. When I write H2, you understand this is a molecule, H2. Just H is atom, representing hydrogen atom, and H2 is molecule. So 1 dozen H2 means 12 H2. Like the bananas, this thing sense, it's an example got sense. The number and dozen also same. 1 dozen H2 equals 12 H2. Any problem? Surely not. Now I'm going to add another thing here. What is that? Consider hydrogen molecule H2. Here's H2, you say H2. How many atoms in a molecule? This is just one molecule. Consider one molecule. How many atoms there? Yes, just two. Just two atoms. This we call diatomic molecules. Hydrogen is a diatomic molecule. Two atoms together makes this molecule. So again, how many atoms in a molecule of hydrogen? 2. So now here I have 12 molecules. See, 12 molecules. How many atoms? How many atoms? One molecule consists of 2 atoms. Then how many atoms in 12 molecules? Surely I write 12 into 2 is 2. Am I clear? Because per molecule consists of 2 atoms. Now here will be A's. Here will be A's. That means again 12 molecule of hydrogen consists of 24 A's, because each of the molecules consist of 2 atoms. So 12 molecules consist of 24 atoms. Now I'm going to represent this number as 24 in dozen. How many dozens are here? How many dozens could be? 12 into 2. How many dozens? Surely here you say 1 dozen equals 12. So I'm going to write here 2 dozens. 2 dozens of what? A's, hydrogen atoms. Clear? The thing is again, 1 dozen H2 equals 2 dozen A's. This could be possible because suppose here we are 12 persons. 12 persons have how many legs? 12 into 2 is 24. Yes, 24 legs. 24 legs. How many dozens? 2. Yes, 2 dozens. That means 1 dozen of people have 2 dozens of legs. 2 dozens of legs. Is there any problem? No. It's natural. It's normal. So what's the wrong here? When I write 1 dozen H2 and that equals 2 dozens H, is there any problem here? Shouldn't be. This thing I'm giving we already know, but we're just gonna use this concept to understand more. Now I'm gonna change a little bit to convert this into mole estimation. Come on, here's no more dozen. I cut this dozen. Now I write here mole. 1 mole of H2. I'm gonna write 1 mole of H2. Here's given 12 H2. No, this is not possible. This is 6.02 and 10 to the power 23 H2. Like 1 dozen H2 equals 12 H2. Similarly, 1 mole H2 equals 6.02 10 to the power 23 H2. Okay. Now look at the hydrogen again. 1 molecule consists of 2 hydrogen atoms. How many molecules I have this time? Avogadro number 6.02 10 to the power 23 atoms, 23 molecules. 6.02 10 to the power 23 molecules. How many atoms are there? If 2 atoms in one molecule, and then you will surely get double number of atoms. 2 into 6.02 into 10 to the power 23. This is 8 atoms. That means again this number of molecules, that means 1 mole hydrogen, and then this double number of hydrogen atoms. Come on. 2 into this number of hydrogen atoms, and this number means always what? 1 mole of is 1 mole. Okay, so we can write here 2 moles. 2 mole of ACE. What is here? That you get 1 mole of H2 equals 2 mole of ACE, hydrogen. These two substances are actually different. When you consider H2 and ACE, not same. H2 is molecule and ACE is atom. I hope you understand. It's about mole concept. Now another thing I want to add here. 2 other things, closely related things are also here. These are molar mass and molar volume. Molar mass and molar volume. Molar mass. Okay, come on. I have started with giving examples of 12 of pens in my pocket. So it's looking heavy. Actually, no pens here. You just imagine 12 pens together. 12 pens together certainly have mass. What is that? Okay, let's measure its mass in a balance. So we can measure mass of 12 pens together. That would give certainly certain mass. And here let's go to apply this concept, the same concept for this number of molecules. As you see here, this number of molecules, when this is 1 mole hydrogen, I write again, this is 1 mole of hydrogen. When I go for writing 1 mole of hydrogen, that gives it. One mole of H2 equals this number of H2. This number of H2 together. We already know that hydrogen molecules are tiny, very tiny. Their masses, real masses, are also almost negligible. Cannot be measured with balance with current system. They can be measured with relative to carbon scale, surely. But here we are consider real mass of this number of particles together. This is possible. Like you can measure mass of 12 pens together. You can also measure this number of molecules together. Yes, you cannot measure mass of 1 molecule alone because you cannot even catch this. Even you cannot see this. It is so tiny. But when this number of molecules together, it would be little big amount, real amount that you can see, that you can measure. Yes, we can measure what mass when this number of particles together. Suppose this number of hydrogen molecules together, this will give certainly a real mass in gram. I show you. So consider this is a balloon, and when this number of molecule is inserted in this balloon, the balloon will be big in size, really big, really big. So 6.02 10 to the power 23 number of H2 molecules given in this balloon. The balloon will be like a healthy person. Okay, come on. So what do you get? Consider the mass of the balloon. This will increase, surely increase. Mass of the balloon will increase. That means increase means the balloon alone without the gas certainly has mass. And when you insert this number of molecules in the balloon, the mass will be different and that will be greater. And subtracting these two, I mean balloon with this gas, hydrogen sample, and balloon without anything. Okay, subtracting these two masses, you get mass of this number of particles together in the balloon. So that is called molar mass. Why? Because this is the mass of 1 mole. So mass of 1 mole, molar mass. Molar mass means mass of 1 mole. Here we get, in this balloon, here is 1 mole hydrogen, and this has a mass that we can call molar mass. Come on, here hydrogen 1 into 2, this we get 2. This is relative mass of hydrogen, and relative mass of hydrogen means 1 hydrogen molecule, just 1 hydrogen molecule is measured compared to carbon scale. It's 1 molecule of hydrogen. But when here, considering the balloon, there is not 1 hydrogen atom, here so many hydrogen molecules together, and here the mass will be 2 gram. Like the relative mass 2, this is for 1 hydrogen molecule, and when Avogadro number of hydrogen molecule together, we can call 1 mole together in this balloon, we say this is 2 gram altogether. So it is 2 gram is the molar mass of hydrogen, and just 2 is the relative mass of hydrogen. So I hope this is clear now. What is molar mass? Yes, another thing, like 12 of anything, 12 pens, 12 marker, 12 bottles, they're all 12, all 1 dozen, but will they have same mass? Surely not. Surely not. 12 pens smaller and 12 water bottles bigger. So consider mass. Mass will be different. Similarly, when here not hydrogen, say you are now inserting big molecules, carbon dioxide. Carbon dioxide, this number of carbon dioxide 6.02 10 to the power 23 carbon dioxide molecules are there in this balloon now. Do you think the mass will be same? No, because each of the molecule carbon dioxide is bigger than hydrogen. Okay, come on, we consider what's the relative mass of carbon dioxide, CO2. 12 is for carbon, oxygen 16 into 2, that we get 44 without unit. This is mass of single molecule. But when this number of molecules of carbon dioxide together, this will have real mass, can be measured with gram. I show you 44 gram. That means when you insert the 1 mole carbon dioxide in the balloon will increase its mass by 44 gram. That means mass of 1 mole carbon dioxide is 44 gram. So these two are the examples of molar masses, and molar masses are same as the relative masses of the substances. The difference is just 2. One, when let's consider relative mass, the mass of single particle, single molecule or single atom, and when you consider molar mass, this is not single, it's Avogadro number of molecules together. And another difference, this is having any other unit, no unit, because this measured compared to carbon scale, and this being measured with real scale, gram. We measure molar mass, we can measure in gram. That is, here carbon dioxide is 44 gram. Now is another last point is molar volume. What is molar volume? This is very simple. What is molar mass? Mass of 1 mole of any substance. Molar mass, mass of 1 mole of any substance. What is molar volume? Volume of 1 mole of any substance. No, here's little change, that is volume we consider only for gas. Liquid has volume, solid has volume certainly, but in the estimation gas volumes are significant. So by molar volume, by the term molar volume, we always mean the volume of gas, and surely this is of 1 mole. What is that? Let's see here, the examples already given. This is a balloon, and this balloon has 1 mole carbon dioxide in the balloon. 1 mole carbon dioxide, 6.02 10 to the power 23 molecules together in this balloon. This is 1 mole and this has mass, this is 44 gram. Consider now volume. Don't you think the balloon will have a volume? What is that? This is 24 dm cube at RTP. At 25 degrees Celsius and 1 atm pressure, the balloon is supposed to be 24 dm cube. So what is here in the balloon? 1 mole carbon dioxide gas, and that occupies a space we call 24 dm cube. What you may call this? Molar volume, molar volume, molar volume. This is molar volume. Again, let's change the gas. This was carbon dioxide. Mass was 44 gram. Now we change. Let's take another gas. You can consider hydrogen. Hydrogen 6.02 into 10 to the power 23. So now in this balloon you see 1 mole hydrogen, that is 6.02 10 to the power 23 molecules of hydrogen together in this balloon. Mass would be 2 gram as I've shown in earlier. Mass would be 2 gram, that's a molar mass. But volume, what do you expect? Generally we may expect the volume should be a little less than 24 because carbon dioxide is bigger molecules and hydrogen smaller. Don't you think that the volume will be? No, the volume will be same. And this is interesting. Volume will be same, 24 dm cube. Amazing, yes. You may think that 12 pens together, it has a volume. 12 pens together, solid pen together, it has a volume. And 12 marker together, can you think these two have same volume, same space they will occupy? Surely not. But this is possible for gases. When this number of Avogadro number of carbon dioxide molecules were together, the volume occupied was 24 dm cube, that we call molar volume. And when this is hydrogen, tiny molecules, number is same, and we also call this 1 mole together, the volume is still same. How come? Okay. Here is intermolecular space. When molecules are bigger, then they are closely spaced in the gas. This is actually the fact. When these are tiny particles, hydrogen, the distance between the molecules are a little more than carbon dioxide. Because carbon dioxide bigger molecules, intermolecular attraction is little greater there, so molecules are closely spaced, occupying total volume that is same, that is 24, that we call molar volume. You can consider this room, classroom. We have classroom. How many students here today? Is 35, yes? 35 students in the classroom. Do you think if the student number is 55, what would be the size of the room? Same. Yes. For us this is same. And if this number is only 10, the number volume will be also same. Also same. And now we consider, if you consider here 35 not people, 35 small thing, suppose 35 of bottles in this classroom. Now consider size of the room, same. So what's the difference here? That 35 bottles will be well spaced, far away from each other, and 35 people were consistent. Like here in molecules, when you consider hydrogen molecules, this number together in this balloon, there will be littles away from each other. But if this is carbon dioxide, not hydrogen, the number of molecules also same. We still call this molar mass, mole, but volume occupied will be same. That is 24 dm cube. Surely, molar masses are different for different substances, but molar volume of different gases same, whichever is the gas. So we summarize today today's class, somebody says, what is mole? Mole like a dozen, a certain amount that has Avogadro number, that is 6.02 10 to the power 23 number of particles, and that is mole. And when this number of particles together, this will have mass, real mass. If you measure the mass in gram, you will get some mass, that is called molar mass. And if you put this number of particles, if this is gaseous, in a balloon, it will occupy some space, that is 24 definite, at definite conditions. This 24 dmK we call molar volume. Okay, this is